Okay, thank you very much. Once again, we're looking at coupled models, and as I said early on, probably the overlap between what's been in some of the sort of model and system talks and this application talk, maybe the distinction between different things isn't always clear. So some of what I say today, I could well have said yesterday. But I'll introduce some sort of complementary material to things that I talked about and trying to focus on the sort of application and impact aspects and how we communicate some of those things to different users, whether that's kind of expert users or public communication. So that means there'll be a fair bit more talk about the NAO that I was talking about yesterday, also tropical cyclones. So that's kind of how I'm going to work through things again, looking at the different timescales we've been looking at for the last few lectures. So the short and medium range, seasonal, decadal, and then out to climate timescales. And as before, there'll be some sort of overlap between some of those things because many of the systems we're using are at least similar, if not the same. I just put a few sort of introductory comments about coupled models and their sort of impact on users. Actually, of course, users don't necessarily care which system forecast products come from. They don't care whether your weather forecast came from a coupled ocean atmosphere model or not. What they want is the best quality forecasts possible. And often the requirements of users, however you want to class them, users or public, are sort of unrealistically high. And they have different ideas of what best quality means. Fabrice was helping us think about quality indicators this morning, but lots of people have different ideas. And for some users, actually, I think this was something Fabrice didn't mention this morning, but also came out of some of the CMEM's sort of user forum work, is that actually users don't want things to change too often either. If you spent a long time kind of working out how some particular impact in your downstream system correlates with a forecast of ocean currents from a particular product, then you don't want that product to change too often. So these can be sort of competing requirements from our point of view. We want to make the most of improvements in the science, but at the same time, we do have to be careful about the way that we then bring those through into systems and how we communicate that to users. And actually, we've talked a lot about coupled systems. Actually, it may well be that users are less concerned about whether products coming from a coupled system, but what they really want is a kind of coupled distribution of data. So they want to be able to go to the same place and get a consistent set of data or a consistent or a complete set of impact advice from different uncoupled systems kind of pulled together. So that may well be much more important than the systems themselves. For some users, consistency between those things will be very important, though. So if you pull together a load of data from different systems on the same portal so users can make use of it, then they may care if it seems like the surface meteorology that you're providing is inconsistent with the sea state information, is inconsistent with the surface currents, for example. And I'll mention that briefly in a moment as well. Coupled applications, I think, are often, like many applications, kind of regional, coastal, small scale. And it's on those kind of scales where coupling of multiple model components is probably most important for these kind of impacts. That doesn't mean that coupled global models and larger scale models aren't important. We've seen lots of examples of that already. And even for these systems, they're going to be providing improved boundary conditions, for example, and forcing for the more detailed models. So kind of a lot of what I've said there sort of touches upon these ideas of actually it's not just seamless modeling systems where we maybe use the same coupled model on all time scales that are important. People talk about seamless forecasting services. So actually being able to provide a forecasting service which for the user is kind of consistent across all timescales, regardless of where the information is coming from. So information on these different timescales, this is just a schematic from a UK MetOffice document, but information on these different timescales will be used for lots of different aspects of planning, financial trading, for example, agriculture, water planning, the short timescales, emergency response, weather warnings, for example, adaptation to climate change. So all these kind of things provided as a seamless service, drawing on lots of different models, some of which may be coupled models, some of which may be uncoupled models. And this is a similar sort of schematic, just to show that it's not people like the MetOffice alone who talk about these kind of things. This is from the US, looking at a similar sorts of ideas on different timescales, using different modeling systems, some of which will be coupled, an increasing number of which will be coupled, but not all, on different timescales, feeding through together to give kind of consistent impacts. So this is the other way around. So in this case, forecast timescales are up there, and these different sort of impacts are on the axis at the bottom. And so actually pulling together some of these things for users from a whole variety of different models, some of which are not models we would deal with at all, some of which are just observations, so like earthquakes in this case, I think is increasingly kind of the way forward. So this is just a sort of prototype internal system at the Met Office which tries to pull together lots of hazards from different modeling systems on different timescales. So you've got things like the tropical cyclones, you've got indicators of heat waves and anomalously cold conditions. You've got indications of extreme precipitation. These areas are showing precipitation over the preceding, I think, 30 days in this case. And lots of different information from both ensemble systems and deterministic models. So these kind of coupled sort of delivery of impacts is probably as important for users as where your actual model information came from in the first place. But I'll now get back into the main sort of thrust of what I'm going to talk about and these different timescales and different applications on those timescales. And again, as I say, I'm going to talk quite a lot about both NAO in these sections and also tropical cyclones in that section. So this was a slide I showed yesterday, just kind of indicating on a statistical basis that that our high-resolution couple models do a better job of the forecast track of tropical storms in the North Atlantic than the uncoupled version. But of course, kind of that's of interest, but users are always kind of more interested in specific cases. So I just thought I'd pull up a few sort of examples just illustrating what we've seen in our system. So this is the recent cases for Hurricane Irma, which I guess most people are familiar with, just illustrating the differences in track between the coupled model and the uncoupled model. So the coupled model's in blue here, same resolution atmosphere as the deterministic numerical weather prediction system that we run at the Met Office. These are kind of as much to illustrate as that there isn't that much impact on the track. So you see it in these kind of statistics, but in an individual case, of course, the differences are usually relatively small, particularly if the sea surface temperatures aren't playing too much of a part in what's going on in the track. So in this case, we saw, and this was information that was provided to the National Hurricane Center alongside our normal deterministic model, which they make use of. So in general, the couple model did show us signs of keeping the track slightly further west as we went through the days leading up to the event, which did turn out to be a slightly better track prediction than the uncoupled. And in all cases, we saw this usual trend that the deepening of the storm was slightly reduced in the coupled system compared to the uncoupled. But of course, so coupling has an impact, but it's still within the sort of envelope of the uncertainties which the National Hurricane Center would put together based on a whole load of different models internationally, including ensembles. So on an individual basis, you can't say that the coupling is necessarily beneficial, but we've seen that in general it is helping. And it's probably worth noting at this point that the ECMWF track predictions are basically considered the most reliable system globally, at least. And from next year, as I mentioned, they're going to have a coupled deterministic and ensemble from day one in the tropics. So I think we'd expect to see further improvement in their storm track predictions next year. I just put a little plot. Some of you may be aware that there's a lot of talk about Hurricane Ophelia heading across the North Atlantic at the moment, and predictions for the track of that and whether it's going to go up towards the UK. This was a couple of days ago. The track seems to have shifted a bit more northerly, so southern Europe seems to be safe. But the UK always gets very excited when there's talk of a hurricane or ex-hurricane heading up our way. But again, you see that the tracks of the coupled and uncoupled versions are pretty consistent. And that's what the National Hurricane Centre think. As I've already said, a lot of the applications of coupled systems will be regional ones. I'm not going to say much more about that really, but we've seen a number of examples from people this week, including the Meteo Tsunami example locally. And I've put coupled reanalysis in here as well as an example of an application of kind of coupled operational oceanography. It's got clearly potential for better understanding the past climate over the last century. It's useful for initializing other coupled systems, so seasonal and decadal systems will be a user of coupled reanalyses. But it also, going back to this point I made before, provides consistent information on surface meteorology, surface ocean, and if you've got a wave component, then also the wave model. And I think things like that are increasingly important for users. If you've got some sort of ocean infrastructure which is sensitive to thresholds in all these different aspects, then if you're provided with sort of 3 inconsistent reanalyses that haven't been coupled in any way, then it can be difficult to feed those through some kind of statistical impact model to draw conclusions about maybe the vulnerability of a particular system. So having that consistent information for some users is actually probably more important than necessarily the absolute quality of any one of those pieces of information. And I think coupled data assimilation, which I talked about a fair bit previously in the context of the short-range systems and the fact that it generally isn't being used yet in those systems, for the reanalyses, it has been progressed more quickly. And I guess one reason for that is if you're moving towards a coupled reanalysis, well, a coupled system for a reanalysis, then the only choice is coupled data assimilation because you're not running a forecast, so you can't do a coupled forecast and uncoupled data assimilation. So that's really the only way you can move towards a coupled system for the reanalyses. And one of the things that makes it easier is that you don't have the issues of when you're receiving the observations, which for ocean observations and the different cycling that tends to get used for ocean systems causes complications, as I talked about yesterday. And I think particularly in data sparse periods, the fact that the coupled data assimilation allows you to use observations in one component to influence the other is potentially of particular importance. So these slides were from the ECMWF coupled reanalyses. I think I may have showed these, or Keith may have showed these previously. So they've been doing 20th century coupled reanalysis with ocean, sea ice, wave, and land and atmosphere. And certainly Keith illustrated this before, that they've seen improvements in latent heat fluxes over the ocean, for example, and a general heat flux balance, which seems much more consistent. And that seems to be partly because the era 20th century had a bit of a shift in the wind forcing. And of course, in an ocean-only reanalysis, there's nothing in the ocean which can then feed back on the wind and help that to adjust, so you get a sort of spurious trend, whereas in the coupled reanalysis, things seem to stay better in balance, and a consequence of that is that the net temperature increments are reduced. So again, seems to show improvements in the coupled reanalysis. And there've been similar sorts of work in the Japanese reanalysis, where again they seem to have shown improvements in the net heat fluxes. So the general heat budget of the ocean is improved. What was seen to be excess of latent heat in the previous system has been reduced. So similar sorts of results. The system's more in balance. These net heat fluxes are more in balance. I'll move on to seasonal systems now. and look at a range of timescales. So this is what people would often call subseasonal, in fact, sort of out to about 30 days, and some of the ways that these coupled systems are used for information for users. And this is a kind of regime-based, weather regime-based product that we produce at the MetOffice, actually mainly using ECMWF data, I think, where you cluster the sort of atmospheric conditions into a whole variety of regimes. I'll just put a bit of a zoom so you can see some of those in a little bit more detail. But these are looking at the most probable regimes in the UK for this particular time of year, then showing from the different ensemble members which of those for days out from day 1 out to day 30, which of those seem to be the most likely. So those kind of probabilistic regime-based products are very useful for users who are able to make use of the probabilistic information. And we've seen these kind of plots for things like ENSO in previous talks from Mike, and I think I showed some yesterday as well. So we make these sort of ENSO plume plots available from our system, and then those things get pulled together into kind of multi-model outputs as well. And the various initiatives which pull together those kind of long-range multi-model ensemble forecasts from different centres around the world. So this is a WMO one. But something we're starting to hear quite a lot about, and many of you have probably heard about, is climate services, which it's one of those things, a bit like coupled modelling. It's quite difficult to define exactly what climate services is. But this is how the EC define climate services. So transforming climate-related data and other information into customized products such as projections, trends, economic analysis, advice on best practices, development and evaluation solutions, and any other climate-related service liable to benefit that may be of use for the society. So pretty all-encompassing, and that's really on timescales from seasonal through to anything longer than that. I think Martin mentioned the global framework for climate services this morning, and then within the EU there are things like the EU Copernicus Climate Change Service, C3S, which some of you may be aware of, and as part of that, things like seasonal forecast products based on different systems. So in this case, MetOffice, ECMWF, Météo France are made available. So again, we've got I think up to date or last month, ENSO, SST, anomaly plume, and an ensemble product for the sea level pressure anomaly over the coming month, I think. So that's for the next month. You might ask the question, what's going to happen for this winter, because I've talked a lot about NAO. Now, most of the NAO forecast information I've shown has been November forecasts for December, January, February. So October's a little bit early to have too much confidence. But I thought it'd be interesting just to have a look what our system's showing at the moment, which is signs of a positive NAO, so higher than 50% probabilities of a positive anomaly in the Azores region and a negative anomaly further north. But we'll see, that may not happen. Tropical cyclones on seasonal timescales. Our seasonal system has shown good correlations between the model in red and the observations in black for the number of storms. Now these have to be normalized because our seasonal forecast system, as I showed you yesterday, and most seasonal forecast systems around the world are only maybe 50, 60 kilometer atmosphere, so they can't represent anything approaching a kind of realistic looking tropical storm. But they can still provide good skill in predicting the numbers of storms over the years. So these are from the MetOffice system, as I say. And again, I just thought I'd bring it up to date with what's been happening this year. So this was our forecast issued in June for the storm season this year, June to November, looking both at the number of storms and also this thing called accumulated cyclone energy, which is really a better indicator of the sort of total number of storms, well, the total strength of the storms during the season, because it takes into account both the strength and the duration of the storms. So you'll see that in both cases we were predicting something above the long-term average. And this is actually a multi-model forecast using both MetOffice and ECMWF forecast output, and I think was consistent with some of the other seasonal forecast output around the world as well. So quite significantly, particularly for the accumulated cyclone energy, we were going for something above the long-term average. Now, actually, it's been massively above the long-term average. So we were suggesting 145. We're already well above 200 as of a few days ago, whereas climatology would say we'd only be about 100. So it has certainly been a pretty extreme season this year, and I think in the top 3 or 4 in the satellite record at least. More generally for seasonal forecasting, at least until recently, it's tended to be kind of what you might describe as a sort of consensus forecast approach for example, for the UK and for Europe. So drawing together information from, for example, the MetOffice dynamical seasonal forecast system, other models, statistical models that we've already heard a bit about from Mike, observations, looking at some of the known drivers of climate in the UK, expert opinion, and sort of bringing all those things together. And I think they will all continue to have a role. But increasingly, as seasonal forecasting using coupled models advances and the skill of those models themselves is improved, some of these other aspects perhaps have a lesser role. Mike was talking to us about the fact that dynamical forecasts for ENSO are now comparable or are exceeding statistical forecasts in terms of skill. So we're starting to see that actually you can go from this step of kind of observations of tropical ocean temperatures to ENSO prediction using a model rather than using a statistical relationship. We're starting to get models like the MetOffice seasonal forecast system, which can go from ENSO and other drivers of predictability to things like NAO prediction using a forecast model rather than any kind of statistical relationships. But I think this last step, going from things like the NAO to the actual impacts on the climate, for example, European winter climate, is still usually tackled with a statistical relationship. And that may be because the models themselves can't directly represent these impacts. Perhaps the models don't have enough complexity. They just don't have those Earth system components included in them, or they don't have the resolution to do that well. And the signals are also weak, partly because of that signal-to-noise ratio issue that I talked about before. So at the moment, this last step from sort of modes of variability to climate impacts is often still using a statistical relationship. But I think over time, that one will also start to become more and more something where you draw the impacts directly out of the model rather than having to infer what's going on. So for the UK, for example, pulling together all these kind of pieces of information, we try to provide advice to relatively expert users. So these are things that go to sort of Cabinet Office, for example, and to government, trying to put the sort of probability distributions from the model for a particular year in the context of its climatology and in the context of observations. But inevitably, there's a fair amount of kind of cautious language to make sure that these aren't interpreted too deterministically, even though that can be the tendency. But there have been quite significant successes recently coming out of the skill in the NAO forecasts, and particularly warnings about winter 2015-2016, that there was a wet signal, an increased storm risk, and then a shift to colder later in the year. And those things were realized, and so it's certainly useful advice coming out of these systems. But a lot of the other examples of seasonal forecasting are coming out of correlations with the NAO. So in these cases, I'm going to show the next few slides. They're examples where people have looked at a particular aspect, so in this case, UK river flow, they've correlated that with the NAO, and then they've used the NAO predictions from the model to provide skillful predictions of, in this case, winter river flow. So it's not river flow that's being taken directly out of the seasonal forecast system. And there have been various other sort of user-driven applications that have been examined. So this is looking at winter airport disruption, so correlating both to the observed NAO, and again you get correlation relatively high, and then correlating to the forecast NAO from the seasonal forecast system. You can provide skill in forecasting these impacts. And of course, things like winter transport disruption at airports are massively costly, so any information you can provide about that is very useful. This is an example of energy demand, again looking at correlations with the NAO and using those to provide skillful predictions from the model. And this is going somewhere other than the UK and Europe, just for a bit of variety. In this case, I think it's using model output directly rather than correlating with any other aspect that the seasonal forecast model is predicting. But again, seeing skill in predictions of rainfall in the Yangtze River Basin and being able to use those for information, particularly looking at the Three Gorges Dam. And there's been more work looking at various aspects of energy infrastructure across China as well, impacts on wind energy, solar energy and the like, and showing skill for some of those. Bringing it back to the ocean, because I've maybe been talking a little bit too much about the atmosphere, you can find various correlations, for example, on the northwest European shelf between sea surface salinity and sea surface temperatures with the NAO on various different timescales, so lagged correlations, and so there's therefore potential to use those predictions of skillful predictions of the NAO for predictions of some of these aspects, and I guess then feeding from those things like biogeochemistry. Moving on to decadal timescales. I'm not going to say too much about this, but there's also been work looking at tropical storm predictions on decadal timescales. So looking at the decadal system hindcasts and correlating those with North Atlantic storm numbers. So these are hindcasts initialized in November one year, and then looking at storm numbers from June to November the next year, and then in the years after that as well. And one thing we've seen in this system is that if you look at anomaly correlations between these storm numbers in the different systems, you see that actually the initialized decadal forecast system is significantly better than the uninitialized forecast system and always better than persistence. It's worth noting that the reason as you go through these forecast ranges, so these are looking at the first year, the first and second year together, the first and third year together, etc. So these are increasingly long period averages of the number of storms. And over those periods in the season, in the hindcasts that we're running in our system, there is a trend due to other forcing in the system, so anthropogenic forcing, natural forcings from solar variability and the like. So that's partly what gives us the predictability over these longer timescales. But certainly initialization of the system and the deeper ocean correctly is also helping. And of course, these are very important for sort of insurance, reinsurance industries, both on these timescales and the shorter timescales that I've already talked about for tropical cyclones. And then finally, climate timescales. I showed this plot yesterday, which is a sort of traditional IPCC climate projections with various different emission scenarios and showing an ensemble of different products from different models from different centres. But these kind of top level information about mean temperatures are of limited use, and the IPCC itself and other organisations are increasingly looking about how regions and extremes are going to be impacted by changes in climate seen more generally. And and there's an EU climate projections project just starting or just about to start, I believe, which is building on some of the work that was done for UK climate projections in recent times. And that was attempting to include lots of different sorts of uncertainty in these climate projections at a regional and more local scale. So the work that was done in the UK used a whole combination of different IPCC, a couple of climate simulations with different emissions scenarios. And on top of that, it used a perturbed parameter ensemble for some individual models, at least for the MetOffice model, with an approach where a certain amount of that parameter space was explored directly, and then an emulator was built to represent that parameter space and to be able to sample it in a lot more detail at a lower cost. Some of these things inevitably have sort of controversy associated with how you actually choose to do them, but that was the approach that was taken in this case to at least explore a bit more of the parameter space. And then that information, which is all coming from lower resolution global climate models, then needs to be downscaled to more local scales, and part of that methodology for the UK climate projections was to use a statistical weather generator to do that. And as a result of that, various different maps were produced with probabilities in this case. So this is changes to the mean daily maximum temperature in summer by the 2080s under the medium emissions scenario. And there are a whole load of plots like this which are available from this website, but there's also an interactive tool to allow users to kind of look at in more detail at the things that are most relevant to them and play around looking at, for example, the probability distributions of some of these different changes in different regions. So it's work like this that's going to be extended for the European area under that European project that I talked about. And as part of that work for the UK, there was also a marine element which involved downscaling some climate model ocean fields. So from HADCM3 in this case. So this was quite an old model, as represented by the fact that the English Channel isn't even resolved. In fact, you can hardly tell that that's the UK, but it is. So that model was then downscaled using a higher resolution, in this case, a Polcoms configuration. And this is just illustrating, I guess, what we all know about downscaling, that it's not just a matter of interpolating this onto a higher resolution grid, but the fact that you've got high resolution bathymetry, you've got different processes like tidal mixing more accurately represented. So it is actually giving you significant new information in this downscaled field, which isn't in the raw climate model field. So this is an example where your parent model was a couple model, but actually your downscaling was done in an ocean-only system, whereas there may be other examples where you're looking perhaps on shorter timescales where your parent model is an ocean-only system, but then when you want to look more detail at impacts, you then run a couple model. So that's just by way of illustration that there's not always a sort of coupled for everything strategy. Sometimes you'll have a global couple model and a regional uncoupled model, and sometimes vice versa. So that, in fact, is basically my summary. So couple models are rightly, I think, becoming more common on short as well as long time scales. But I don't think that means they're the answer to every problem on every spatial and every temporal scale. And I think that means we need, as operational centres and those like me who work in those kind of operational environments, but also us as individuals as we're doing our research and working out what we need to do. We need to make appropriate choices for different systems and different applications, thinking through what's actually required. And coupling may well be the answer, but it's not always the answer. So that is the end of my last lecture, I think. Thank you.
Thank you, Chris. Questions, please? So thank you for presentation. So regarding the initial shock, for any kind of forecast, shorthand or long-range forecast, have you been using the same approach to treat the initial shock?
Sorry, could you just repeat that question?
Yeah, because a problem regarding the coupled model forecast is the initial shock.
Yes.
Yeah. So for any kind of forecast, seasonal and climate, have you been using the same approach to treat this initial shock?
So for these longer forecasts, the initialization shock is less of a concern. I mean, there will still be adjustments in the system over the first few hours or days, but they're less, well, we think, I mean, it's not to say that there aren't impacts that we've not really discovered, but we think as long as the individual analyses for the individual systems are reasonably consistent with each other, then there's not a major problem in putting those together to initialize a coupled system.
Thank you.
So thank you.